All right, welcome back to your stats notes. So this unit 6 kind of is broken into two halves. The first half is all about the random variables and combining and transforming random variables. And then the second half focuses on what are called Bernoulli trials. Now, what is a Bernoulli trial? A trial is a Bernoulli trial if the following three conditions are met. All right, condition 1, there are two possible outcomes. And we usually view those as either a success or failure. All right, so either you achieve something or you didn't achieve something. Two possible outcomes. All right. Number 2, the probability of success stays constant. Trial after trial. So it can't be that once you've done something 10 times, the probability changes, or it becomes more likely, or it becomes less likely. The probability needs to stay consistent, whether you're doing it once, twice, or 50 times. The probability of success is the probability of success. Doesn't change. And then 3, the components of the trial are independent. And this one's the trickiest, but we're also going to see that there's some exceptions where we can sort of loosen this restriction because the answer ends up being the same sort of regardless. So again, more important are some of these first couple of ones here. All right, number 1, do these situations involve Bernoulli trials? So we roll 50 dice to find the distribution of the number of spots on the faces. So we're counting how many 1s, how many 2s, how many 3s, how many 4s, how many 5s, how many 6s, right? This would not count as Bernoulli because there are more than 2 outcomes. You could get a 1, you could get a 2, you could get a 3, you could get a 4. We're already past 2 outcomes, so that doesn't work. Number 2, how likely is it that in a group of 120, the majority may have type A blood, given that type A blood is found in 43% of the population? All right, so we're just going through the people one by one by one. Do you have type blood? Yes or no? Do you have type blood? A blood? Yes or no? Do you have type A blood? Yes or no? If we go through this, there are only 2 possible outcomes. Either you have type A blood or you don't. It's either a success or a failure. The probability of finding type A blood stays constant, 43%. All right, so that should stay steady. Doesn't matter how many people I check. If that's like the, worldwide constant for type A blood, it doesn't change as I start working through people. Last, the components of the trial are independent. So assuming we're not talking about like 120 people that are related, then person A's blood should have no impact on person B's blood, which should have no impact on person C blood. Like just because I tell you that person over there has type A blood, it doesn't tell you anything about the person 7 spots over. All right. So this one would be yes. All conditions are met. We deal 7 cards from a deck and get all hearts. How is that how likely is that? So we deal the first card. Is it a heart? Yes or no? We deal the second card. Is it a heart? Yes or no? We deal the third card. Is it a heart? Yes or no? So we're meeting the success failure condition, but the probability is not staying the same. No, because we're drawing without what's called replacement. We're not putting the card back. So the probability changes. All right, the odds of getting the first heart is 13 out of 52, but the odds of getting the second heart is 12 out of 51. The odds of getting the next one is 11 out of 50, and so on and so forth. So the probability is not staying constant. All right, suppose you repeatedly draw cards without replacement until you draw an ace. All right, same situation here. All right, so no, same reason as above. And then last but not least, a company realizes that about 10% of its packages are not being sealed. In a case of 24, is it likely that more than 3 are unsealed? So again, we're looking at the package. We're saying, is it sealed or is it not sealed? Yes or no, success or failure. Okay. The probability stays constant. So if the company says, hey, it's just 10% of the packages that aren't being sealed, then yeah, that 10% is constant. It doesn't change as I work my way through the case. Now, the last one there is the part that we'd have to know more about their manufacturing process. Like, do the ones that become unsealed kind of clump together, or are they randomly distributed? So we can say yes, as long as unsealed packages are randomly distributed. If they tend to clump together, as soon as we find one, we know that we have a better chance of finding other ones, and then this condition is violated. But if each box is totally independent of one another and it doesn't, that the sealings or unsealings don't clump together, then this one would be fine. All right, so this is what it takes to be considered a Bernoulli trial. Now, we examine Bernoulli trials in basically 2 settings. One is the geometric probability model. One is the binomial probability model. All right, this is the one we're going to focus on today, the binomial, and then we'll focus on the geometric one next class. So what are they? All right, so the geometric probability model is used when a random variable counts the number of Bernoulli trials until the first success. All right, so it's basically how many tries does it take to succeed? All right, geometric probability model is looking at how many tries does it take to be successful. The binomial probability model is used when the random or a random variable counts the number of successes in a fixed number of trials. So just to compare these again, this is, hey, I'm doing something 10 times. How many times was I successful? This is saying, hey, I'm going to keep doing this until I'm successful. How many tries did it take? So in this one, I don't know how many times I'm going to try. I just keep going until I'm successful. This one, I know how many times I'm going to try. I'm going to try 10 times, 15 times, 20 times, and then let me count how many times I'm successful in those tries. All right, so really quickly before we delve into the binomial, let's just make sure we can tell the difference. So how many 6s do you expect to show up if 10 dice are rolled? Right, so you're defining the 6 as a success, everything else is a failure, and you're counting how many 6s you got. So that would be binomial. You are playing a board game and you need to roll a 1 to win the game. How many turns do you expect to take before you roll a 1? Right? In this case, we don't know how long we're going to have to do this. We're waiting for that first 1. So that would be geometric. A basketball player has a shooting percentage of 70%. If she takes 30 shots, how many baskets do you expect she would make? Again, you're counting the successes. So that would be binomial. And then a basketball player has a shooting percentage of 25%. How many shots do you expect him to take before he makes 1? Again, that time you're counting how many tries you have to take. So that would be geometric, right? And it's just important to be able to tell the difference because we're going to have to use different calculations. We're going to have to use different formulas. We're going to have to use different things on our calculator and so on and so forth. All right, so let's dive now into the binomial probability. And we'll take a look at the model and the formula that sort of drives the calculations that we're going to do. So first things first, let's establish some of the variables we're going to be using. N is going to be the number of trials. So anytime you see N, we're talking about the number of trials. All right. P is going to be the probability of success. Q is going to be the probability of failure. And you can always find Q because it's just 1 minus P. Remember, there's only 2 options. So if you have a 30% chance of succeeding, you have a 70% chance of failing. All right. And then X is going to be the number of successes in N trials. All right. So the formula that we're going to do with this is the probability that your random variable X is going to have some number of successes. So 3 successes, 4 successes, 5 successes is equal to N choose X, which is combinations. This is basically the number of combinations. So what does that mean? Well, let's say you want to find out what are the odds that I make 2 out of 5 shots. Well, I could miss the first 3 and make the last 2. I could make the first one, miss the next 3, make the last one. I could make 1, miss 1, make 1, and then miss 2 more. But this mathematically will give us the total number of combinations to achieve 2 out of 5 successes or to achieve 10 out of 30 successes. And we usually read it as like, let's just pretend it's 5 again, 5, choose 2. We're going to multiply this by the probability of success raised to the number of successes you want times the probability of failure times the number of times you would fail. All right, so this right here represents the probability of any one combination. So let's think of it this way. Let's say I'm a 30% free throw shooter, and I want to know what's the probability that I'm going to make 2 out of 5. Well, whether I make it like this, where I make the first 2 and then miss the next 3, or whether I miss the first 2 and then make 2 and then miss 1, doesn't matter how I rearrange those are always going to work out to be the same thing because you're multiplying the same numbers. So this gives you the probability of any one combination. This tells you the total number of combinations possible. So if we take the total number of combinations and we multiply it by the probability of one of those combinations, we're going to get the total probability. Now, this is basically what we're doing. Side note here, where NCX equals n factorial over x factorial n minus x factorial. All right. And again, we're not going to do a lot of this by hand, but I just want to show it to you so that you at least know where it's coming from. Now, factorial is when you like take the number and multiply everything below it. So like 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So anyways, this n choose x, this is how that's actually calculated. All right, it's the factorial of n divided by the factorial of x times the factorial of n minus x, and that'll give you the number of combinations possible. All right, so this is the formula we're going to be using. Again, on the next page, we'll show you how you actually use it. The only other things that you need to know about this is that the mean of a binomial distribution can be found by doing n times p, and the standard deviation of a binomial distribution can be found by doing the square root of n times p times q. All right, so this formula, we're actually going to end up doing a lot of this on the calculator, but this is explaining what the calculator does. So you're not actually going to need to memorize this formula. You are going to need to remember both of these pieces here. All right, this we're just going to use at the very start to kind of visually show you what's actually happening. These you need to know and kind of commit to memory. So let's take a look at an example here. Suppose 20 donors come to a blood drive. 6% of all donors are universal donors. So we're going to answer a bunch of questions of, how many universal donors can we expect? Can we expect 2 universal donors, 3 universal donors? First thing we have to check is, does this meet the qualifications for a Bernoulli trial? So condition 1, success, failure is a check. All right, either they are universal donors or they're not, so we're good there. 2, the probability is constant. All right, we're good there. All right, 6% of all donors, that 6% stays steady. And then 3, the people are independent. So again, assuming they're not related, one person's blood has no impact on what another person's blood is likely to be. So our components are independent. We don't have to worry about things like clumping together or stuff like that. So how many do you expect to be universal donors? So that's our mean, which sometimes we do use this symbol. All right, that's our population mean, which is just n times p, which in this case is 20 for our sample size, and 6% are universal donors. So we would expect 1.2 universal donors on average. Now, what is the standard deviation? Again, sometimes you'll see this symbol for the population standard deviation. It's the square root of n times p times q. All right, so again, this is mean. This is standard deviation, just in case. And then that is going to be the square root of 20 times 0.06. And then the problem didn't give us q, but we know that p and q have to add up to 1. So q is just going to be 0.94. And we get all 3 of those. we can multiply them together on our calculator. So 20 times 0.06 times 0.94. Take the square root of that. Type it in correctly. 20 times 0.06 times 0.94 and get 1.06 roughly. 1.06. So this says, what is the probability that there are 4 universal donors? All right, so if we're using our formula here, this is basically saying, okay, 20, choose 4. How many different ways are there to organize it so that we have 4 successes out of 20 trials? Now, the probability of any one of those outcomes is the 0.06 to the 4th power, because you had 4 successes, times 0.94 to the 16th power. All right, so if we go and we start to type this in, so we can go to 20, and then we can go to math, probability, and you're going to see this NCR. So I type the 20 in first, then I type in the 4. All right, I'm just going to hit enter right now so that you can see that. There are 4,845 ways to select 4 successes with 20 different people. All right, so there's a lot of the different ways. Now, each of those ways has the same probability. It has 0.06 to the 4th power times 0.94 to the 16th power. All right, so that's really small. All right, any one of those combinations is really small, but there's 4,845 of those combinations. So altogether, it works out to be, like 2.3%. All right, so 0.0233. Now, down here, it says, what is the probability that there are 2 or 3 universal donors? So again, it would just be 20C3 times 0.06 to the 3rd times 0.94 to the 17th, right? Those 2 exponents are always adding up to the number of trials, plus 20C2 times 0.06 squared times 0.94 to the 18th. All right, and again, we can type those in. I'm just going to type it in all as one right now. So 20 math probability, 20 choose 3 times 0.06 to the 3rd times, whoops, got to get out of the exponent there, times 0.94 to the 17th. And that gives us like 8.6, 0.086. So this one is 0.0860. And then this one down here, again, 20, math, probability, NCR, choose 2 times 0.06 squared times 0.94 to the 18th. And that gives us 22.2246. 0.2246. So when we combine those, 0.2246 plus 0.0860, we get a combined probability of 0.3106. All right, so that's the formula of what's actually happening. Now, a lot of times we're not going to use this long formula. All right, I show it to you so that you can see it, but in actuality, we're going to let the calculator do most of this work. So we're going to use something called Binomial Pdf and Binomial Cdf. It's in your distribution menu, same place as normal CDF, and it's down towards the bottom. So there's Binomial Pdf, Binomial CDF. Both of these need 3 pieces of information. They need their trials, they need the probability, and they need the x value. Now, this calls it x value. A lot of other places, you'll see it listed as NPK. So again, I'm going to write NPK on the notes here. It might show up as x value on your calculator, but in stats books, you can see it both ways. So I just want you to be exposed to both ways. So I'm going to write NPK, but just realize this can also just be what we think of as x. N is your number of trials. P is your probability of success. And K is the number of successes you're testing for. All right, so it needs those three pieces of information, which makes sense. All right, if we look at the formula, there's the number of trials, there's the number of successes, and then the number of failures we can figure out on our own, but we do need this probability. And then we can figure out this probability on our own because it's just, this one's just 20 minus 3, this one's just 1 minus the 0.06. So this is the information the calculator needs to be able to plug into this formula. Now, Binomial Pdf is when you're looking for the probability of a single event. All right. So I could redo this problem up here as a binomial PDF where there are 20 trials and the probability of success is 6%, and I want to know the odds of getting exactly 4 successes. And if I put that in there, 20.064, you're going to see that it gives me that same 0.02333 that I got the first time. So I don't care whether you do it the long way. Nobody ever chooses to do it the long way, but you're welcome to, or use the calculator. But if you're going to use the calculator, this is the work that you show. You say that I'm using BPDF, I'm doing 20.06 and 4. On something like this, you could just say, hey, I'm doing BPDF, and I'm doing it once for 20.06 and 3, and then I'm adding to it the BPDF of 2. All right. So if that's what BPDF does, what is BCDF? Well, let's bring up the menu. And the first thing you'll notice is it asks for the same exact information. All right, so it needs the same exact NPK as up above, and they all mean the same exact information. The only difference is this is looking for the probability of a single event. This is for when you're looking for at most. And what I mean by at most is i.e. less than or equal to some value. So it could be less than or equal to 3 or less than or equal to 4. But when you do a binomial CDF of like 4 successes, it gives you the probability of 4 plus the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0. All right. It only goes in a downward direction. So what that means is if you want to do something like greater than 3, generally you have to do something like 1 minus binomial CDF. Can be used for greater than situations. All right, by default, binomial CDF does less than or equal to, which means if we want to do a greater than situation, we have to manually do it by doing a 1 minus. And we're going to do an example on the next page, and you'll see what that looks like. All right, so a certain tennis player makes a successful first serve 70% of the time. assume that each serve is independent of the others. If she serves 6 times, what's the probability she gets all 6 serves in? All right. So this one we wouldn't even actually need to use the formula on because there's only one way to get all 6 serves in. So it's basically just 0.7 to the 6th power, but we'll do it anyways. Pdf, there are 6 trials. The chance of getting one in is 70%. We want to know the chances of getting all 6 in. Now, again, because of the way the formula is set up, this is really just the same as doing 0.7 to the 6th power. And you're going to see that whether I do that, 0.7 to the 6th power, or whether I do this formula, Binomial Pdf, 6.76, you're getting the same answer. All right, so I just want to show you that those two are the same in that situation. Now, once you get to something like this, it's not as straightforward because there's multiple ways to get 4 serves in. So this one, we're just going to go straight to using Binomial Pdf. There are 6 trials. The odds of getting one in is 0.7. We want to know what are the odds of getting exactly 4 in. So again, we go to our distribution menu. We go to PDF, 6.74, and it gives us 0.324135. 324135. All right. This one says no more than 4 serves in. All right. So no more than 4 serves in is saying, okay, you can get 0, 1, 2, 3, or 4. All right. But no more than 4. Now, this is exactly what Binomial Cdf does. All right. If I do a Binomial Cdf and say 6, 0.7, 4, it's going through and it's finding each of these probabilities and adding them together. And it just does it for us automatically instead of us having to type in all 5 of those separately. All right, so 6.7 and then no more than 4. So we get 0.57. Whoops. 0.579825. Last but not least, at least 4 serves in. So at least 4 serves in is saying 4, 5, or 6. Now, Binomial Cdf doesn't go up. It only goes down. So this is the part that kids usually goof up. But let's pretend that these are all your possibilities. 0, 1, 2, 3, 4, 5, and 6. You can get in 0 serves all the way up to 6 serves. If we want to know the probability of getting at least 4 in, 4, 5, or 6, we only need to subtract away 0, 1, 2, and 3. So it's going to be 1 minus Binomial Cdf. And even though the problem says 4, we're going to do 6, 0.7, 3. Because by subtracting away 3, 2, 1, 0, we are left with 4, 5, and 6. I'm going to put a little star here because this is the one that gets goofed up the most. So 1 minus, then I go to my distribution menu, Binomial Cdf, 6.73, paste that in there, and I end up with 0.74431. All right, so that's how you use the binomial feature on the calculator, and we're going to have lots of questions that sort of deal with this. Now, I said at the very beginning that when it came to Bernoulli trials, there was a little flexibility on the whole independence issue. All right, here's where that flexibility comes in. All right, it's called the 10% condition. which states that it's still okay to proceed without independence as long as the sample is smaller than 10% of the population. And this is important because when sampling in the real world, it's almost always performed without replacement. So you're selecting people from a group, and technically, once you select that one person, you've slightly changed the balance of the group, which has changed the probabilities, which is technically a violation of the Bernoulli Trial. So we have this sort of rule of thumb that says as long as your sample is less than 10% of the population, it's going to be close enough that we don't actually care. Now, let me prove that to you. A music distributor inspects an SRS of 10 CDs from a shipment of 10,000 music CDs. Suppose that 10% of the CDs in the shipment are defective. All right, count the number of bad CDs in the sample. Technically, this isn't a binomial setting because once you select one CD, the odds governing the next selection change. All right, find the probability that none of the 10 CDs selected are defective. All right, so if 10% are defective, and the shipment is 10,000, that's implying that we have 1,000 defective CDs. Now, we can use that to say, all right, if there's not 1,000 defective CDs, then 9,000 of them are okay. So in my sample of 10 that I'm selecting, because it says I'm taking an SRS of 10 CDs, the odds that the first one is fine is 9,000 out of 10,000. The odds that the second one is fine is now 8,999 out of 9,999 because I've taken one of those CDs away. It's not constant because I'm sampling without replacement. All right, the odds that the next one is good is 8,998 out of 9,998. And I'm not going to write these all out. I'm going to just do one of the little classic dot, dot, dots there until we get down to the last one. That's 8,991 over 9,991. And if we multiplied these all out, it would be 0.3485. You're going to have to trust me on that or do it yourself to verify. Now, let's take a look at the binomial situation. All right. Our population is 10,000. Our sample of 10 is less than 10% of 10,000. All right, so we meet this 10% condition. There's a lot of 10% going on here, but this 10% has nothing to do with this 10%. So we meet our 10% condition, which means even though technically it changes, the binomial calculation is going to be pretty close. So if we do a binomial Pdf and say, all right, what are the odds that in 10 trials where if 10% are defective, 90% are fine, what are the odds that all 10 are totally fine? All right, because again, if 10% are bad, 90% are good. So in a trial of 10, where 90% of the CDs are good, what's the chance that all 10 are going to show up good? Now, again, this is another one where we could just do 0.9 to the 10th power because there's only one way to get 10 out of 10. But just to show you that it gets the same thing, we're going to do binomial Pdf, 10 trials, 0.9, 10. And you'll see that both of them give us the same 0.3487. So, not the same, but pretty close. Which is why we kind of say, all right, as long as this condition is met, this is way easier to do, and it gives you more or less the same answer. So we say that it's close enough. because again, in the real world, you're almost always sampling without replacement. So if we literally held ourselves to the standard of the Bernoulli trial, we'd almost never be able to use it. So this gives us a little flexibility to be able to use it. All right. Another way that we can be a little flexible is that the binomial distribution can sometimes start acting like a normal distribution. All right. And in fact, the Bernoulli distribution can get a little cumbersome as the numbers get large. Now, this isn't really an issue on computers anymore, but it used to. Used to be an issue. So the normal approximation still has its value, but it's not as important as it maybe once was. Anyways, if the numbers get large enough, instead of using a binomial, we can actually go back to using a normal distribution. Now, how do we specify what's big enough to use a normal distribution? Well, we establish what's called the 10 success, 10 failure condition. All right. And this basically says for a normal model to be a good approximation of a binomial model, so for them to effectively give you the same answer, we must expect at least 10 successes and 10 failures. So what does that actually look like? N times P has to be greater than or equal to 10, and N times Q also has to be greater than or equal to 10. And again, P is the probability of success, and Q is the probability of failure. And again, I'm just going to do the same exact thing I just did. I'm going to prove to you that we pretty much get the same answer, whether we use the normal model or whether we use the binomial model, because once this condition is met, they're going to give you pretty similar answers. So this one says basically an email monitoring company says that 91% of email messages that get sent out are spam. You recently install a spam filter and observe over the past week, it only okayed 151 out of 1,422 emails and classified the rest as junk. Should you worry that the filter is too aggressive? Is it accidentally filtering some of your real email? To answer this question, check the following. What is the probability that no more than 151 of your 400 or 1,422 emails are real messages? All right, so first let's do it the binomial way, and then we'll compare it to the normal way and see what we get. So no more than, this is a Cdf situation. And if 91% of email is spam, so if 91% is spam, then 9% is real. So this is asking, what are the odds that you get no more than 151 real messages? So that's basically Cdf when we're talking about 1,422 trials. And the odds of success are at 9%. And we want to know what's the odds of getting 151 successes or fewer. All right, that's what Cdf does. It does from 151 down. Now, kind of what I was saying before, why this whole normal approximation thing came to be is 1,422 C 151 is a gigantic number. Like if I put this into my calculator, it's going to give me an overflow error because it's too big. All right, now it can still handle the Cdf, but again, you just start dealing with giant numbers, which is why this came into being. So Binomial Cdf, I've got 1,422 trials. The odds of success is 9%. I want to know what are the odds of having 151 or fewer. All right, and if I do that, I get 0.9837. All right, now let's compare that to the normal way. Now, before I can do that, I have to verify my condition. So I do 0.91 times 1422, and I do 0.09 times 1422. All right, I need these both to be bigger than 10. So 0.91 times 1422 is way bigger than 10. 0.09 times 1422 is still bigger than 10. So 129.4.02, 127.98, both are above 10. All right, so that's what I needed to see there. Now, to do a normal distribution, I need the mean and I need the standard deviation. So the mean we know is n times p when we're in this binomial setting, and the standard deviation is the square root of n times p times q. All right, so our n times p, we actually already did that. We did it right here. It's just the same 0.09 times 1422, which gives us 127.98. And then this one's the 0.09 or the 1422 times 0.09 times 0.91. All right, and if we take the square root of that, square root of 1422 times 0.09 times 0.91, we're going to get 10.79. So 10.79. All right. Let's go a little further. All right, because by rounding it, we are going to lose some accuracy here, which might make these answers a little more different. So we'll at least go 4 decimals here. So now that we have these two values, we can say, all right, what's the NCDF of negative 9999 to 151? All right, so same thing. We're doing 151 and down when the mean is 127.98 and the standard deviation is 10.7917. All right, and if I bring this up, NCDF, negative 9999, 151, 127.98, 10.7917. I'm going to get 0.9835. All right, so again, very similar. So as long as this condition is met, we can actually basically fake the binomial distribution with a normal distribution and more or less get the same answers. All right, so that's it for today. Again, kind of the big ideas here is this idea of a Bernoulli trial. And then you don't have to know this formula. You don't have to use it. It's just to kind of show you what the calculator is doing so that you're just not mindlessly going into the calculator and you have an appreciation for where some of these answers are coming from. All right, and then we kind of have these two exceptions. This is an exception to get us around independence as long as your sample is less than 10% of the population. And then this is if we want to use the normal model instead, if we kind of want to sub out the binomial model for a normal model, we can do that as long as this condition is met. All right, so that's it. If you have any questions, let me know. Otherwise, have a great day.